Good. So basically, what I'm going to try to convince you today is that taking taking stochastics into account, so making basically or extending the possibilities that we have, or extending the toolbox to find solutions to say more realistic / relevant problems is very much is very similar to what we did before. And to show you that, basically the plan of today is that I just walk you through all the things that we already did without stochastics, and then show you that we have basically the same results, however with minor adjustments. I mean, they are minor adjustments. You will see that later on. And the so to say minor adjustment is that we have to take expectation operators into account. This sometimes makes the finding of the numerical solutions a bit more demanding in some respects. But as I said, the general idea, so the general structure, will remain the same. Okay, so what we were looking for is, we said, or which problem do we face? Well, we want to maximize, as always, some intertemporal utility function or some intertemporal objective function. Whether this is utility, whether this is profit, that doesn't really matter. So we have a sum of contemporaneous objectives, okay? And we want to pick, this is what we can do. We want to pick a specific control path. Say you have one control variable, then we want to pick the optimal control path given the situation that you are in, okay? And the trick in all those intertemporal problems is that obviously the thing that you do, so what you control, affects your situation that you are in tomorrow. And with taking stochastics into account, we would just argue that the effect of your doing on the situation that you are in tomorrow is not perfectly known. It's not deterministic. That doesn't necessarily mean that you do not know the impact of your doing on the situation you are in tomorrow. It could also mean that you know that you know the exact impact of your doing today on your doing tomorrow, but that there will be some exogenous shock. Okay, so you can frame this in a number of ways. And what we assume here is that we basically have a notion, a model of how this stochastic influence would look like. So we would be able to tell something about the stochastic structure of this shock. Okay, this will be important later on when we do the numerical exercises, but this will also be an important starting point when we talk about the reinforcement learning. Okay, so what do we want to do? Well, we want to. This is obviously a random variable, so maximizing random variables is a little bit difficult. We want to pick highest numbers, so to say. So we have to transform this random variable into a number, so to speak. And how to do that? Well, we just apply the expectation operator. So basically what we do is, in a sense, we stack together deterministic problems, okay, and then pick the optimal, and then look for the optimal control path. And again, here the situation, everything within this bracket, so within this expectation operator, looks exactly the same as what we had before. You know, the only difference is that here's an additional variable, epsilon t plus 1. But note that within the expectation operator, this is just in one part of the sum. This is just one realization. So for any realization, this is like a parameter, right? So this doesn't really change. And the thing now is, we want to pick. We talked about that. So the issue is, you want to weigh all those sums with all the with all the probabilities with which you expect the epsilon t's will realize in the future from now on until capital T. But that obviously you do not have to pick the control, so the plan of the controls at time 0, but that you sequentially choose these objects. So basically what you want to do is you want to maximize the Lagrange function as we did before, by choosing every control at every point in time, and by choosing every state at every point in time, taking this dynamic restriction into account. So as before, we would just like to take the first derivative of the Lagrange function with respect to CT, with respect to all CTs, and with respect to all STs. Okay, but the thing here is that we have to adjust the expectation operator. Why? Well, because at every point in time, we already know the history. So, for example, if you want to pick the optimal control at point in time 8, okay, you do not necessarily have to maximize or have to maximize this expression, okay, because this is based on the information set in 0. So this is like saying you have to pick the optimal control in year 8, given the information that you have in 0. But this is not necessarily true, right? As time evolves, you can change your plan, right? You can adjust your control at any point in time. So you only have to take a stand concerning the control at point in time 8, when really point in time 8 arrive. But then you only have to pick, or you only have to consider the expected value given on the information set at point in time 8. But then your objective, your contemporaneous objective, is just a number. Okay. So having said this, you just take the first derivative again. Note the second bullet point here: choices are sequential. So if you take the first derivative of the Lagrange function with respect to any CT, you obviously do not have to apply an expectation operator on the contemporaneous benefit, okay? Because when you are in point in time 8, you know what the instantaneous utility will be once you change your control. This is this. What you do not know, obviously, is the effect of your choice of today on the rest of your planning problem. So you need to consider here an expectation operator, and please observe that this expectation operator is also conditioned on all the information that you have at point in time t. Okay, not necessarily in point in time 0. Again, you do not have to write down an explicit plan at point 0 for everything you want to do in the future, but you go step by step. Okay, and this is basically the condition for optimally moving step by step through the problem. Okay, the thing here is usually, and this makes or this might make those things a little bit more difficult, that the shadow value is a random variable, and the change in the state due to your choice is also a random variable. So potentially what you have here is you have a random variable times a random variable and a crazy potentially nonlinear function of a product of two random variables. So that might be difficult. Usually we just by some simplifying assumptions we circumvent that. But note that this expectation operator always looks very innocent, right? But once thinking about it, you come to the conclusion, well, maybe it's not that innocent. Okay, you do the same for the state that you would pick. So basically, this tells you what would happen if you experienced a windfall gain in the state at point in time t. And basically, this is again the first derivative of the Lagrange function that we had. However, again, only considering the future as being uncertain. So everything that is contemporaneous is known to the agent, because we, as I said, we plan sequentially. And the only difference to what we had before, I mean, just if you would look at it on a very ignorant level, then you would say, well, the only things that differ are this E and this E there. Okay, this is the only difference, and this just tells you that you have to trade off the contemporaneous effects that you're doing has with expected future effects. Okay, this is the thing. And what you then would usually do is you would stack those first order conditions again together to get eventually an expression that tells you something about how the optimal control path evolves. But note that we do not have just one control path. Okay, so we cannot say something about the slope of the optimal control path, because there is no ex ante optimal control path, because the control path, or the decision of the decision maker, obviously always updates the information set. Okay, so at every point in time, obviously I can think about, given the things I know today, what would be the optimal control in 5 years. But this is not necessarily the optimal control that I would pick once I am in 5 years. Okay, but this is not a problem. Okay, this is not a thing of time inconsistency, but this is just a thing of additional information. Okay, as you move through the problem, you learn things. Okay, and then you update what you do. So this being said, there's no point in deriving one slope of your control path, because there are basically many control paths, so to say, or many controls depending on the realizations of your random variables. So what you are basically after is you look for an expected slope of your control path, of your optimal control path. Okay, and this is basically what we want to do. And the simplification that we already had before, we have a linear impact of the control on the future state. We have this linear impact of the current state on the future state, and we assume that utility is not a function of the state itself. And we assume that the epsilon is also linear, as a linear effect on the st+1. So it would be like st+1 is some function of the state that you're in today and the control plus some shock. Okay, and putting all this together is a great simplification using the first order conditions that we just had, and then we can derive again a Euler equation, or a Keynes-Ramsey rule, or whatever you wanna call it, that is again very, very similar to what we had before. So without the expectation operator here, we would be back again to what we had before, right? Then so without this expectation operator, this would tell you something about the slope of the optimal control path. Again, this is not possible here. So what you have is you have an expected slope of the optimal control path. This is what you can do, right? So if you would like to solve for the control path, you cannot solve just a regular differential equation, but you would have this more complicated stochastic the differential equation that you could solve. This is not the approach that we are after here, because we do something else. But in general, it would yield the same result. Okay, this is just to again show you. Okay, this is very similar to what we had before. Okay, so the only difficulty is what would be, how could we apply this expectation operator? What does it mean? What does it say? And how can we retrieve it when we want to do it numerically? Okay, this will be the challenge that we will face later on. Okay. Okay, now again, this is what I've told you. We have no deterministic, so we do not have one solution. We don't have one path, but we have basically many control paths, and basically we follow those different control paths as we move along through time. So the control path by itself is a stochastic process. So we could, using the underlying stochastic or the underlying stochastic structure of the shocks, let's call the epsilon shocks, we could also derive, at least in principle, the stochastic properties of the optimal control path, and then we could say something about that. Note that this obviously, you know, if you really had to do that, it could become very difficult and very cumbersome. But you know, in this conceptual thing, this is not the question whether this is difficult or cumbersome. The question is, would it be possible? And the answer is obviously yes, it would be possible. Having those information, you could use this information to say something about the optimal control path as a stochastic process. You could describe that. Okay, this is just the general idea. Okay, I've told you, and this will be true as well here, that we are not necessarily using the Lagrange approach as an appropriate way to finding the solution. It was again just to show you that in general you could solve this at first glance difficult problem with methods and things and tools that you already know, right? Most of you know the constraint optimization techniques. Most of you are maybe somewhat familiar with expectation operators and with stochastic processes, and using this information, you could solve those problems. It would take a lot of time. It would be super tedious and cumbersome, but you could do that, right? This is just the message that I want to send with the Lagrange approach. So for you to see, okay, well, it's not super different to what we know, to what you already know. Okay, when we talk about the dynamic programming approach, in the deterministic case, I told you that this is basically just a different point of view on the same problem, and the idea there was not necessarily to directly describe how the optimal control path would look like, but we were very much keen on thinking about how the optimal control would be, or what the optimal control would be as a function of the state that we are in. Okay, this is basically the picture that I try to tell you. What we are after is basically a large spreadsheet with two columns. So with the states that you are in column one, and the controls that you want to pick in the second column. And maybe this plan applies for every point in time. So you would just look it up in your Excel spreadsheet plan, and would see, okay, the state that I'm in today is 8. So the best thing to do is, I don't know, 3. Okay, and you know this for all the states. Now, obviously, with this taking stochastic into account, this might necessarily not do. Maybe this is not the helpful information that we need, but maybe we, in addition to that, also need all the realizations, all the past realizations of the shock. So sometimes it might be helpful, but not all, a finite history of all the realizations of the shock. And what this basically means is, when picking the optimal control, I'm not necessarily only be looking at the state that I'm in currently, but also I'm looking at the way that I reach this state. So what I need is, I basically need a larger spreadsheet, right? The idea is the same. Okay, I'm looking for the optimal plan, but the spreadsheet must be larger. And what I would like to know is, I mean, this is the elusive quest, right? What I would like to know is, how can I describe this functional relation? So how can I know, how can I derive this functional relation that tells me what is the optimal control? Okay, depending on things, and this is basically what we are looking at. Here we have a situation where we focus on just a finite history of all the past realizations. Okay, so this is n is a vector of length n, right? Or is it n plus 1? I'm always confused with it. No, it's n, right? So the vector of length n, which is finite, and this is just all the past realizations that you have. This is a somewhat general assumption, okay? And we will see later on that I mean, except that we do not consider infinite histories, that we for the moment relate to this relatively general notation, relatively general assumption. But we will later on, when it comes to applications, make this a little bit, so this assumption a little bit easier. And we can do this by restricting the nature of the stochastic process, basically. Okay, because maybe a sneak peek into what is coming. We had this expectation operator, right? So basically what we need to have is, we need to think about the probability weighting. So we need to think about what is the probability for any of those states. And sometimes it's important in some problems that this probability is a function of the history of the process. At least of the finite history of the process. Sometimes it's not. Then you have independence. Then things tend to be much easier. Okay, at least this is my perception. But the general idea still applies. So even if you have a situation where you want to consider the history of the process as being relevant for everything you want to do. Okay, and in some applications, this is obviously important that you know the history of the process. Although to be honest, I'm not. Has anybody of you guys a good example of when that would be the case? So just from scratch, a good example where you would say, okay, I have a situation where you want to focus on the history where you arrived at some state.
Well, it could be, for instance, the past policies or the past prices set by some competitor over the, well, depending on the time horizon you look at, over the past hours or so.
So because this will reveal some information about your optimal behavior and about probabilities of how the prices would be in the future. This is basically the thing. Yeah, this is a good example. This is a good example. Okay, but at first glance, this might look very technical, but stick with me for the next half an hour or so, and you will realize that it's really the same. I promise. To the things that we did before. Okay. Do you have questions so far? Okay, so this is basic.
Sorry, maybe one more example. Sure. In finance, and some of you are from finance, sometimes you're not only interested in the expected future path, but also in the risk. And if you have a model concerning the risk structure, like a gauge process or something, then knowing the past values, the past returns in that case will give you some information about the risk that's going to be in the future. So in that case, you would be interested in past realizations, past returns, because they will give you some information about the stochastic structure in the near future, even if they are not correlated in the sense that you have a good prediction for the future level of returns. That doesn't really matter in this case. You might have information about the future risk of the returns. So in that case, also, you would be interested in the past history of the returns.
Okay, thank you. So let me stress that again, right? This is basically the solution. This is what we are after. So this is due to the dynamic programming approach, but this was also the case in the deterministic part. We just say take a look at the problem from a different angle. Okay, we say, suppose that we knew the optimal plan, what to do for every realization, for every state, for everything is super. Then we can write this as a recursive structure, and we basically change, instead of looking for the optimal control, what we're after, we're looking for the optimal value function. Okay, because this is easier to retrieve, and once we know the optimal value function, well, then we can answer this question. Okay, so don't be too confused saying, oh, well, but how can we, is that of any help? Well, it's not, right? It's not of any help. It's just saying, suppose you knew the optimal thing you want to do, then you suggest, and then you think that this is a function of the state that you are in and the history that you experienced. And we see later on when this will indeed be the case, right? This is maybe important that this does not confuse you too much, because actually what we then can do, we can take these optimal controls and plug this into the objective function, right? So this, I think there's a slight notation thing, because this CT star is the same as this CT. Okay, we've just shown that this is the optimal choice by making this a function of the state and the past history. So basically, what you do is, if you know what to do, you could plug this into your objective function and take your objective function is the contemporaneous utility for every realization, okay, of the absentees at every point in time, so of all the realizations that we have, and take the expectation operator, right? And since the expectation operator is a linear operator, so the expected value of a sum is the same as the sum of the expected value, we can just swap the expectation operator and the summation operator. So basically, the optimal situation that you are in, or the value that you would attach to this problem once you follow the optimal plan, is just the sum of all the expected contemporaneous utilities. Okay, and once we know that, we are done, right? This is what we are after, and we can write it that way, obviously. But again, this is not very helpful at first glance. Okay, but later on we will see that by changing the perspective, this makes this rewriting helpful. But again, this was the same that we discussed with the dynamic programming again, except for the expectation operator. Okay, and for the epsilons, we just assumed all the epsilons to be 0. Right. What you could do here as well, okay, you could also assume all the epsilons are 0 and with certainty. Then you are back in the deterministic case that we discussed before. Okay, so using this again, we can rewrite this objective function and again take advantage of the recursive nature of this problem. So what we want to do is, or what I want to do is, I want to show you how to get from there to the value function, or to the function that defines the value function. Okay, so we have we want to pick the optimal policy sequence here, and so what we want to do is we want to define the value function as the expected objective. So this is the objective function following the optimal control path, and the optimal control path is obviously a function. So the control at every point in time is a function, not necessarily obviously, but is a function of the state that we are in and the past history that we realized. Okay, and note again, this is a relatively general notation. Okay, so again, this is the same as we had before, except for this and except for the expectation operator. Okay, and the thing is, we need this notation, so we need the past history potentially, depending on the stochastic process, because if we take, or if we apply the expectation operator on the objective function and we knew the optimal control path, it could be the case that this is still a function of the history of the process, because all the probabilities that you use to calculate this expected value are also a function of the history of the process. Okay, this is maybe that doesn't make sense now, but you will see that later on, hopefully, that it makes sense. Okay, so since you want to weigh all those situations, all the future situations, weigh them with the probability with which they occur, okay, it might be the case that all those probabilities are a function of the past history of the process. So the expected objective that you achieve, given you follow the optimal plan, is also a function of the history of the process. Okay. Again, in some situations, we will see that later on as well. That doesn't really matter. For example, if you have independence of realizations, well, then the history doesn't matter. So past realizations just do not matter. So the probability for every realization is just a function of those realizations, and the expectation operator basically sums those out. Okay, so they do not occur here anymore. So the shocks do not play a role. So the only thing that you need to know is the state that you are in. Okay, but in a more general case.
Sorry to interrupt. Maybe we also need to stress that it's not only the history dependence that's relevant here for the shocks, but if you compare this function here with what we did in the deterministic case, then in the deterministic case, we were maximizing over the future consumption values. So that was a sequence of values that we were maximizing over. And we chose the sequence of values that really maximize the future utility, or the current utility, the value. While here we do not maximize over consumption control values, but we maximize over control functions or control policies. So here we choose the optimal policy CT as a function of the state and the past shocks.
Yeah.
So that's the main difference. Yeah. I think that's even more important as a difference than the shock history dependence.
Yeah. Okay. That's true. So this is but this just occurred to me. So this is no notational confusion. This is correct. So this is just any path and any function that you could choose. So I was wrong with that. So what you basically choose is, as Mark correctly pointed out, that we do not want to find a sequence of numbers, but we want to find basically a functional form that depends on the state and the past history. That's true. That's true. So we are after a more complex object, basically. Or the solution would be a more complex object.
Because in that case, even if I don't know what's going to happen in 10 periods, I already now know that I'm acting according to a certain rule in 10 periods.
Yeah. And
this rule I can decide now.
Yeah. Yeah. So I think this is an intuitive way. So we are not looking for numbers that we want to do, but a more complex rule that takes in this case the state that we are in and the history of the process into account for every point in time. Yeah. Okay. So this is a definition. This is basically, again, from the structure, the same definition of the value function that we had before. Okay, and what we now can do is we can again basically split up this sum into two parts. Okay, into the contemporaneous part, so everything that happens today, and into the rest of the planning into the rest of the planning period. This is done here very in great detail, basically. So we have this sum. We split this up into the contemporaneous value and into the rest value, and then we know that, well, the rest value is obviously again the same. Okay, is again once we follow the optimal plan, is obviously again then the value function starting in tau plus 1, so in the next period. Okay, and what we then can do, we have the sum of everything that happens today and everything that happens in the future, and we wanna take the expectation over this value. Okay, but we know, again, the expectation operator is the linear operator, so the expectation of the sum is the sum of expectations. So I can look at the expected contemporaneous utility plus the expected rest of the planning horizon. Okay, but the contemporaneous utility, there are only things that I already know, right? I know what to pick now. I know what the state is. I know everything contemporaneously. So the expectation of the contemporaneous utility or of the contemporaneous gain is just a contemporaneous gain. Okay, but what we have to consider here is, again, the expected value of the future value function. Okay, and again, if you go back some slides and look at the definition of the Bellman equation or the value function before, then we did exactly the same. The only difference, again, is this weighing, okay, of the future with its expected value. Okay, so the only thing we need to consider, basically, and this again greatly simplifies things. The only thing I have to consider is what is the basically the situation that I'm in tomorrow, and this is not only, or this does not only refer to the state that you are in, but also to the expected or to the realized shock that you are in. Okay, because once you know that, well, then you know, you could know the value that you are in, and then you only have to trade off again today's situation with the expected tomorrow situation. So basically, the everything that happens after tomorrow is just condensed again in this value function. So everything that you need to know about the future is just condensed, is just in this object. Okay, and this is also true for the stochastic nature, right? You only have to consider, okay, what would be the realization of the next shock. And I do not really care what the future shocks are, because the next shock is basically what is relevant for my plan. Okay, and again, I have to take into account that this realization, okay, might be a function, or the probability for any of those realizations might be a function of the past. Okay, and again, it's not the case that that future realizations do not matter. Okay, obviously they matter, but they are hidden basically in the idea that you look at the optimal value that you achieve once you follow the optimal path. Okay, so this is only again a trade-off between today and tomorrow, which again makes things much easier than, for example, with the Lagrange function, where we sequentially go through every point in time, and basically not only every point in time, but also every potential realization that we have to consider. This is easier here. We only have to consider the next period's realization of the shock. Okay, which is nice. And again, this is the same simplification as saying, okay, we do not have to take into account all the future states that I'm in, but I only have to take into account the effect of my control today on the future state. Okay. Do you have questions so far? Okay, one thing, just again, to be very to be as precise as possible for me on this situation. What confused me a lot when first thinking about that was the fact that I have to take those realizations into account in my value function, because I always thought, well, why should this play any role? Because don't we integrate those out or sum them out using this expectation operator? But this is not true here. If you would write this in a more explicit way, okay, instead of just writing the super compact notation of this expectation operator, you would write any probability for any realization of the epsilon t plus tau plus 1. Okay, so here would be a large sum. Say you only had 2 realizations of the epsilon t plus 1, then you have obviously just two parts of the sum, and you would have to multiply those 2 parts of the sum by the probability that the epsilon tau plus 1 is either one or the other realization. Okay, and if you assume that those probabilities might be a function of past realizations, well, then in this more complex writing, you would directly see, well, I have to take obviously this history into account, because it affects the probability that I'm in tomorrow. And as I said, at the heart of this thing is that you want to trade off your control effect that you have on today and on tomorrow, or in this case, on the expected effect that you have on tomorrow. Okay, so this is important. And once you take a different stand on this probability construct, for example, if you assume that it's only a function of last period's realization, or maybe you want to think of that it's not a function of any realization, so it's totally independent, well, this affects which state you have to consider here. Okay, so in this notation, you would say, okay, what is relevant for my planning and for my doing as I move through time is the proper state that I'm in. Suppose the state would be your wealth, okay? And you would also like to consider maybe all the past shocks, all the past shock realizations that you have. So basically what you could do is, in a sense, you could say that this stochastic problem is just like the deterministic problem with more states. So with more states and with a new functional form that you have to take into account, namely this expectation. The rest is the same. Okay, the rest is exactly the same. Finding the value function, looking how this would look like is basically the same. So again, what we want to do is, in everything that we will be discussing next week, is we again want to find the form of this value function. Because once we know this form of this value function, we can solve everything that we have here. We can solve the optimal control for any point in time, for any past history. Everything is done once we know the form of the value function. Again, it's always the same.
Sorry to interrupt. I just come up with an example,
Sure.
and I'm not sure if it is appropriate. Can we consider, for example, the shock sigma is like epsilon? Yeah? Epsilon is like the burst of price bubbles in real estate, like, for example, in big cities in China. And in this case, then the control variable is then like, because like investment in real estate.
Yeah. Yeah.
And because if there is a, then the bubbles will accumulate. So as long as the bubble is, did not burst in the past, then I should consider the accumulation of the bubbles. And in this case, maybe, yeah.
Yeah, that's true. That could be one example. So, for example, in your case, I think the state could be the amount of real estate that you already have, or the value of real estate that you already have, maybe. And the CT is the amount of real estate that you want to buy or sell at every point in time. And obviously the utility that you have is a function of of buying or selling. I don't know, is a function of the payoff that you get, and the payoff is obviously a function of the price. So that would be some sort of a price path that you might want to consider. And you are right, if if you think about your situation today, so what to do optimally, well, then this obviously, or if you want to describe how do you feel today given the optimal buy and sell strategy of your real estate, then this is obviously a function of the real estate that you have and of the past of the past price history. Yeah, that you could do that. You could think about that in that way. That's true. And here, there you would have the assumption that the probability of some price realization in the next period is a function of the history that you already experienced. Yeah, yeah, that is true. That is true. So basically, again, two points. This is, I think, a very in general, this dynamic programming approach is a very flexible tool that you can use, very versatile. It can be applied to many situations. The only thing that you have to be clear in advance is you have to structure your problem in the correct way. So you have to think about what are my payoffs, what are my states, what are my controls, and what is the stochastics and the stochastic and the underlying stochastic process that I want to model. Okay, once you know that, well, then you can go ahead. All right. So as I just tried to tell you, this is a relatively general situation. So we allow we allow for this finite history driving this process, and this is important, I think, because or it's neat, because we have at least two special cases that we can use in the following applying this general form. Okay, and this is very helpful because you do not necessarily have to restrict yourself too much. Okay, for example, you know, I'm more from the pen and paper party. I would be super reluctant to have history dependent probabilities here, because this makes calculating a mess. Okay, so the problems I would tackle are potentially very restricted. Okay, in a numerical sense, this doesn't really matter too much. Okay, because you can basically transform this at first glance very complex situation or structure into the same mold, the same thing, the same construct that we already used. And this is basically what we are going to do. So we focus in the following on two very specific probability structures that we want to analyze. First of all, the one that will be at least closer to my heart, where I would assume independence. Okay, because this solves a lot of problems that you could potentially run into. And the second one would be to just focus on I think first order or higher order Markov processes, stochastic processes. And let me briefly begin with the Markov property. So what we assume here is if the underlying probability structure is such that it follows a first order Markov process, that means that that the distribution of future realizations is only a function of the contemporaneous realization. So we do not necessarily have to consider the entire, not the entire process history of the process, but a large finite number of the process. But we only have to consider the contemporaneous realization. Okay, so basically the probability structure, or the probability, is then only a function of the contemporaneous realization. So basically what we then have here is we do not need to consider the whole sequence of this history, but we only need to consider the realization epsilon tau. Okay, and the same is here true as well. So this is just conditional on epsilon tau, because the probability weight that you use for calculating this expected value is just a function of the contemporaneous realization. So thinking about what is the probability of observing some epsilon tau plus 1, well, this is just a function of the epsilon tau. So this makes this already basically decreases the complexity of the problem. Okay, so this is very helpful. Okay, so what we have so far is we already considered this Markovian flavor because we do not, it's not necessary just to restrict to the first order Markov process, because we can basically transform higher order processes into first order processes. And what we then can basically do, we can put, say, stick for the moment to the first order Markov process. We can we can stack those two state variables just into one state variables. So then what the only thing the stochastic structure would do, in addition to the deterministic case, would be that the state that we are in is higher dimensional. Okay, so the idea would be, if we look at this notation and thinking about the structure as being first order Markov, so then the value function would only be a function of the state that you are in, and of the realization of the shock, or the realization of the stochastic thing that we consider. We call this shock, okay, but it could be anything. That we basically take this together, so we mold this together into a two-dimensional state, okay, and we would call this then the S tilde. And since we could do this as well with all the with higher order processes, as long as they relate to a finite history, we could just rewrite everything that we have, and then we have the situation that the value function is just a function of S tilde, and S tilde is basically the new state. And this is then obviously a vector, because we have to consider all the realizations that we already have, either one or the history of those realizations. And this is called in the slides the proper state variable, which is our usual notion of the state, which is obviously, or which could be obviously, a function of the contemporaneous utility. Okay, but what we then have is, again, we have a formulation of the value function of the Bellman equation, a recursive formulation for the value function, where the value function is again only a function of the state that we are in. Okay, and the expectation is then conditional on the information set in tau. So everything in tau, everything that happened until tau is known. Okay, and we have an idea how the probability structure would look like. And suppose we had a situation where this contemporaneous proper state is not a function, it does not affect contemporaneous utility, and you would look at this equation, then again you wouldn't have too much of a difference to what we had before, right? The only thing again that differs is obviously this expectation operator, but the rest is the same. Okay, we have the value that you experience once you follow the optimal path, given you are in a given the state is S tilde in our case, is just the maximum choice of just the contemporaneous control, where you trade off the contemporaneous utility against the effect of your choice on the expected future. Okay, but this is again exactly the same, more or less, to what we had before. So the solution strategy also would be the same. So we would again in this finite horizon case, start with the last period, solve this problem, plug this in, move one period, move one period back in time, solve this again, and go through this the same way that we did in the finite horizon example that we had. The only difference again is that we have to calculate this expected value always. Okay, but this is again conceptually not too big of a hassle, because we assume that we know the probability structure. Okay, so we know what the probabilities are. We can just plug it in and calculate it. It's more work, it's more tedious, but it's not really more difficult. Okay. The second special case, I think this is the one that we will. I think it's the one that we will consider most of the time, where we have the situation where the epsilons are independent over time. Okay, so the probability of observing some epsilon t, some epsilon tau, or some epsilon tau plus one is not a function of the history of any history of any past realization. And then we even do not have to consider a different this modified state variable as tilde, because here, by applying the expectation operator, we are basically getting rid of the epsilon, right? So so we have the value function of the state that we are in tomorrow. Okay, and we weigh this with the probability of the realization of epsilon tau plus one in this case. But once you would write this down again explicitly, you would see that on the left, on the right-hand side, so here, there's basically, this is not a function of epsilon tau plus one anymore. Why is this the case? Well, because we applied the expectation operator. Okay, so once you apply the expectation operator on the random variable is basically gone. Well, it's not really gone, but you know, it doesn't play a role anymore. It's just a number. Okay, the expectation, well, it's not necessarily a number, but it's you do not have to consider it anymore. Okay, so this makes obviously for a even simpler specification, because here again, if you would compare the deterministic case with the case where we have independent shocks, well, then this looks basically super similar again, except for the need to calculate the expectation over the future value that you might be in. Okay. So the general solution strategy is very similar with the Markov property. The Bellman equation is very similar, except that we have to take this new modified state into account. If we allow for independence, then, well, basically on the form of the value function, nothing really changes. In general, the only thing that changes is that we have to take into account this expectation operator. Okay, but again, everything else that we did is exactly, or that the solution strategy will be exactly the same. So in the finite horizon case, you start in the last period. In the last period, you only have this contemporaneous utility. You choose your control, whatever your optimal control is. You take this optimal control and just move one period back. Okay, knowing that you picked your control optimally. So the only thing you have to worry about is when you are in capital T minus one, what will be the realization of the shock? Okay, because you know, once the shock has been realized, you know what you do, because you have put yourself into the shoes of somebody who is in capital T, who knows what to do. Okay, so basically it's from a conceptual point of view exactly the same. So again, you do backwards induction. The only thing is you have to do a little bit more calculations. But again, once you have the algorithm set up in your computer, well, the calculations are not necessarily a problem for the computer. So the computer doesn't really care whether it uses this value or five sums or five summons and put those together. Okay, that isn't really a huge difference. Okay. Okay. So here we have an example of the solution strategy. I'm not sure. Should we walk through that, or do we wanna look at the concrete example that we have?
No, I think we should walk through that and then do the concrete example next time.
Okay. So basically, what we have is I've written down this situation again. Okay, so we assume independence, and the only thing that I already plugged in is I plugged in the equation of motion for tomorrow's state. Okay, you can see this here. So instead of writing s of it used to be tau plus 1, but here the notation is t plus 1. I've used the definition that st plus 1 is equal to m to this law of motion of st, ct, and epsilon t plus 1. Okay, and here you see that the expectation is obviously over the shock that you are in. But basically, the only thing that you choose at every point in time is the choice between the only trade-off, that you have to consider is what is the effect of your choice contemporaneously today and on the rest of the planning horizon. Okay, and again, this is what I tried to explain a little bit some 10 minutes ago. Also, we only have to consider next period's shock. Okay, so all the other shocks that might happen down the road, yeah, we do not care, because they are condensed in this functional form. And again, as long as we do not know what this functional form would be, this is of no help, right? This is of no help in finding the solution. But what we could do is we could just use backwards induction as we did before. So we just go to the last period in capital T, and in capital T, everything is already realized. Okay, there's no shock anymore. I know what to do, and I know that the value in the last period is just the contemporaneous utility in the last period. So the only thing I do is I just pick my optimal control, which is then just a function of the state that I'm in the last period. Okay, so I know what to do optimally. Okay, then I take this and move one period back in time. So instead of considering capital T, I'm considering the situation that I'm in capital T minus 1. Okay, what is the situation that I'm in capital T minus 1? Well, I again have a contemporaneous utility. Okay, this is just a function of what I do today and of the situation that I'm in today. And I have to consider what will be the situation tomorrow, right? So this is just a function of the situation that I'm in tomorrow. So I could use this, okay, and plug this in here, because this expression is by definition V capital T S capital T, okay, but capital ST is just a function of the shock, okay. So I know optimally what to do. I can calculate this function. I know what this is. And then I can plug in this ST, and then I know basically what to do next. Okay. And again, suppose that the epsilon was just a parameter, so we would have the deterministic case. Well, then we would just take the first order condition with respect to the C capital T minus 1. So we find the optimal CT minus 1 and go ahead. The thing here that we have to consider, obviously, is that we have many epsilon t's. But again, this doesn't really matter. So we take this, we know this, we plug this in and write this down. So we have a sum of all those V capital T S capital T. Okay. Then we can determine what the optimal control would be. Okay. And again, the only difficulty is here that this, before what we had, this was just one expression, but now this is a larger expression. This is just a sum of many things weighted by their probabilities. So this makes it slightly more. We have to invest slightly more time to work this through, but it's basically not too difficult, right? Because you could just calculate this expected value and plug this in. Okay, then you know what to do in T minus 1, and then you go through the algorithm basically. So you would then know what you do optimally in capital T minus 1. You know what the value function is in capital T minus 1, because this is using the optimal control, and you could use this then to go one period back in time and then do the same calculations. And this could be done all over again, and then you would find the optimal path. Okay, and in the independent situation, this is obviously relatively simple. Okay, but again, if you have this Markov process or a stochastic process with Markov properties, again, this wouldn't be too difficult, because okay, you would have a different expression for this expected value, but I mean it wouldn't really change much, right? It wouldn't be too difficult. It would be maybe a little bit more difficult to calculate this expected value, but you would do the same. You would plug this in, calculate the expected value, pick the new control, calculate the new value function, go one period back in time, and so on and so on and so on. Okay, so this is basically what you would do. And again, this again is very well suited, you know, to loop this in a numerical framework. Okay, where you start just at the last period and then calculate everything through. Okay, so we have what we considered so far is a very simple uncertainty structure, but which is in a sense relatively general. So we allow that the probabilities of the realizations are a function of a finite history of the process, or they are even independent. Then things are even more even simpler, and then we can go through things. I think this is again calculating the first order conditions to show that the Keynes-Ramsey rule will be the same. I think we should skip that, because this is not too insightful, because we didn't really work with that. Then I would say we should next week talk a little bit about the betting game and the Stochastic a problem, where we basically apply the this backwards induction strategy to two problems. One is, I think, done by hand. I think I will just talk you through that, I guess, in the first 10 minutes or so, and then you implement numerically an example of this backwards induction approach, taking expectations into account, and then we'll talk just super briefly about the infinite horizon case, and then we have an exercise that is very similar to what we already did, and yeah. So this is what I basically wanted to say today. Are there any questions?
I guess one, just to get this right conceptually. So we've seen 3 Bellman equations today. One was the first one on slide 83 or something, which told us we consider all states up until today.
Yep.
Then 5 slides further, we've simply rewritten this into a state vector. That conceptually nothing has changed here, or has it? Good.
Yeah.
And then the next one there, this is where we change the conceptual view and say, however we got here, whichever temporal differences there may have been in the states before, we don't consider them. They are not important for us. That was the first assumption we made.
Yeah. So this is true. So basically, everything boils down, I think, to the question: when you calculate this expected value, what does the probability look like that you use for calculating this thing? It could be either be a function of a finite history. This is what we assumed here, or it could be just independent of everything that already happened. And these are the two cases that we consider. So one is the situation where these probabilities to calculate this expected value are a function of the finite history. And the finite history obviously could be also just one in the first order Markov process. So this is done. Or you could be more say more restrictive. What I would prefer actually saying, okay, this probability is not a function of any history, it's just super independent, but then this value function is obviously not a function of any past realization whatsoever. So it doesn't matter for the form of the value function what the realization of the shock would be. And these are basically the two things that we consider. And this is I think what you correctly pointed out. Yeah.
Okay, I guess I got it, and thank you very much.
Maybe concerning the terminology, I'm always a bit confused. I don't know what actually is the Bellman equation. So in my view, I use the term mostly for what we can see on this slide here. So we have the value function in the current period, and that just is expressed as the maximum over the control. And then we have the sum of the current utility and the either discounted or expected or whatever continuation value. So this is what I normally call the Bellman equation, but some people use the term Bellman equation only for the infinite horizon case. So I think it's a bit in flux. I'm not sure.
Yeah, I also know basically I would usually also try to only call the infinite horizon case the Bellman equation. I would call this, I don't know, the recursive value function thing or whatever. But I mean, it doesn't really matter, right? I mean, the important takeaway or take home message is, I think, that we have this value function construct and rewrite the problem. And this is true for the Bellman equation and also for this value function thing, whatever you want to call it, and rewrite this just in the into a problem of choosing just one control by just trading off today with the rest of the planning horizon. This is what you always do. So you get you do not have to consider, if I do something today, what will be the impact in 10 years or so? That doesn't really matter. The only thing you have to consider is today and the rest of the planning horizon. Under the assumption that from tomorrow on you do everything optimally. So in a solution wise, this is a tautology, right? It's not helpful. You are saying, okay, if you don't want to have an accident, avoid having accidents. I mean, this is correct, but this is not very helpful. The helpful thing is that by formulating this, we are able to specify basically what to do to avoid accidents. And this is the cool thing, I would think. Okay, but I think overstretched your patience already. Thank you so much. Thanks for having us. And we will meet again on Tuesday. I walked you just very briefly through one of the examples. Super simple. It's very simple, and then you can implement the one of the finite horizon problems into the computer, and then we go to the infinite horizon case, just conceptual wise, super briefly, and then we just code this problem, and yeah, then we are basically done for this year. Okay, thank you so much. Have a good one, and see you next time. Thank you.